Well, good morning, everyone.
Yeah, go ahead. Start. I think everyone's here.
All right. Let me have a very quick review of what we did yesterday. We basically discussed how to go from a continuum quantum field theory, both for scalar models, fermions, or gauge systems, to discretized lattice. Why do we want to do that? What do we gain? If we discretize space-time, we find a mathematically rigorous definition of the functional integral. The discrete space-time will regulate momentum integrals, that is, it provides a regulator for the system, and it allows control to study strongly coupled regimes. That is good enough reason to do the discretization to lattice. I reviewed here very briefly what we did. For fermions, it is simply we define them on discrete space-time points, replace the integral by sum, the functional integral with a product. Gauge fields are a bit trickier. There, the gauge fields sit not on sites, lattice sites, but on lattice links connecting fermions or connecting scalars. And also the variable that we use for gauge fields are not the algebra variable A, but the group element U. The action, as we discussed, can have several different forms depending on how actually we discretize the derivatives. The simplest one that I have written here is contains some of the plaquettes for the gauge field and simply a nearest neighbor derivative that is gauged with the parallel transport. The issue with this Lagrangian is fermion doubling. Fermion doubling is actually deeper problem than it sounds. It is we know that we cannot avoid it unless we either break chiral symmetry or go to non-local, not ultra-local action. I discussed one solution yesterday, Wilson fermions, where we simply add a quadratic derivative to the action, multiply with the lattice spacing, so it's an irrelevant operator that lifts up the zero modes of the fermions. I started to discuss before I realized that I was out of time, another formulation, staggered fermions. Staggered fermions are tricky and interesting. The idea is that we diagonalize the fermions in spinor space. In that case, then we can break up the four Dirac components and just keep one of them. You denote the one component by chi. The price we pay is that the action has a phase factor instead of the gamma matrix, and this phase factor could be plus or minus 1 depending on the site of the fermion. But this is a well-defined action. We have, because we have only one component, it still doubles to 16, but 16 is 4 times 4, so that can be rewritten as 4 Dirac spinors, 4 Dirac spinors, so it effectively describes 4 fermions, not 16. Unfortunately, the 4 Dirac spinors will, the components of the Dirac spinors will come from a hypercube. So there is a shift between the component, and that leads to this splitting. Nevertheless, staggered fermions are very popular in lattice QCD, partially because they have a leftover chiral symmetry, not a full SU4, but only a U1 chiral symmetry, and they are numerically relatively inexpensive, less, or at least less expensive than other formulations. Staggered fermions were proposed back in probably 1980 or even before, And very early on, it was realized that there is a geometric interpretation of staggered fermions. The first papers I am aware of were written by Becher and Yost in 1982, where they understood that staggered fermions are really scalar Dirac fermions, the fermions that we are more familiar with from gravity. They are Dirac scalar fermions, and we know that Dirac scalar fermions are equivalent to Dirac fermions only in flat space and at vanishing gauge coupling. Now that is perfectly okay on the lattice, we have flat space. And when we describe QCD, we are at vanishing bare coupling, so everything is okay. Staggered fermions do describe Dirac fermions. However, at strong coupling, we might have a completely different theory, and that is a very interesting problem that I will discuss, not today, but hopefully tomorrow or next week. There has been a set of work, in fact, let's use that color, by Simon Catterall and collaborators, where Simon has observed that staggered fermions, as written in a scalar Dirac formulation, suffer from a Z4 gauge anomaly. But it's only a Z4 anomaly that can be cancelled when we have two sets of staggered species, two sets of staggered fermions. The consequence of that is that two sets of staggered fermions are anomaly-free, and therefore they can exhibit novel phenomena that we don't see in systems that are anomalous. In particular, they can show confinement without chiral symmetry breaking, and as a consequence of that, they can have symmetric mass generation that is mass generation without spontaneous symmetry breaking, like in QCD, where chiral symmetry breaking leads to fermion masses. Now, that's a very interesting possibility, and I hope to get to it in a hopefully tomorrow or latest next week. Good. It's this possibility that is the possibility that you might have novel phases and new continuum limits. If that can be true only, or that will survive only if we actually have a continuum limit with those phases. That is, we have a system where the correlation length becomes infinite at the boundary of the new phases. So we are back to where we started yesterday. We have to discuss the continuum limit. We have to discuss how, this is okay, how the continuum limit looks, or how we define the continuum limit in a lattice formulation. We know that the continuum limit is associated with infinite correlation length, that is, it has to be on the critical surface. So what we have to ask is, where are the critical surfaces in a gauge fermion system? And then what are the phases, that is, what kind of continuum theory we can define on them. It's also interesting to ask if we can determine the beta function, and I have here only two of them. I don't know what happened to the third, so I will just put it in here. The beta function for confining conformal or infrared phase systems. So we can calculate them perturbatively, as we discussed that yesterday. Can we determine them non-perturbatively? A non-perturbative determination could have important implications, both because we can get the fixed point and also because we can calculate the lambda parameter, the QCD lambda parameter. It's even more interesting if the setup is like that at the conformal system, because what happens here is that we have three different fixed points. And if that is the case, then we should have a new phase on the strong coupling side. I will get back to it in a second, but let's just see, indeed, can we find the phase structure? Can we identify fixed points, critical surfaces, fixed points, and then can we determine actually these beta functions? Good. The method, the approach to do that, the simplest approach to do that is to do to look at Wilson renormalization group in critical phenomena. What is Wilson renormalization group? It really is similar to Continuum RG, but in a more general setup. The idea is that all physics, all important physics in the infrared, in the ultraviolet, we have only irrelevant noise fluctuation. So the idea is to integrate out the UV nodes. That will automatically reduce the degrees of freedom, and we can keep only those degrees of freedom that are relevant for continuum physics, and that is what will lead us to universality. So I have here a quote, I won't spend too much time on it. That was, I believe, from Ken Wilson Nobel acceptance speech in 1975. Basically, it says it's difficult to formulate the RG approach, and one is likely to have to carry out complicated computer calculations, which makes most theoretical physicists cringe. It was true in 1975. Hopefully, it is less true in 2022, but nevertheless, it says it will probably require several years of stagnation before theorists will accept the inevitable of this technique. So let's go and see what Ken Wilson suggested now almost 50 years ago. How does critical phenomena described by Wilsonian RG? Again, the goal is to remove high momentum modes. High momentum or short distance. I will try to illustrate that using scalar fields, but the generalization for fermions or gauge fields is relatively simple. The first step of the process is to introduce blocked fields. Blocked fields are kind of averages. In position space, we can simply take a sum, possibly weighted sum of fields around a given spin. In momentum space, we could simply suppress the high momentum, the fields with high momentum. The capital phi x, capital phi p in these equations are what I call blocked fields. The function f that shows up in both of these equations is some kind of function that is large at small values and decreases for large values, that is, provides this suppression. What do we do with these block fields? We want to integrate the original fields and replace them with the block fields. The easiest way to do that is to take the vacuum functional and simply multiply it with 1. This one is the functional integral of the blocked fields times a delta function that sets the blocked field basically equal to this definition that I have written down there. This is one that it doesn't change the functional integral, but now if we change the order of the integrals and integrate out of the original fields, keep the integral of the blocked fields, we'll get a new expression that we always can write in an exponential form. That will be in the exponent our new blocked action. At this point, it will depend only on the blocked fields, but of course it will be very complicated because we do a very non-trivial integral. So that is how we do that, at least on paper. Let me try to illustrate that in a more, hopefully, straightforward description. So imagine we have the original field here on the left. Every lattice point has a field variable phi. And then we want to form blocked fields. We can form blocked fields by, for example, taking 4 and 4 and 4 and so on, original fields, averaging them, and take the averages. Those will be our blocked fields that I illustrate on the other side. So the blocked fields at this point live only every other lattice site or in the center of the lattice point. This is the step 1 of the real space RG transformation. The scale change now is that I denote by B is 2, because simply the number of fields are reduced from the original to the blocked fields by a factor of 2 in each direction. Now, if we integrate out the original fields, then we are left only with the new blocked fields, the green fields, and that is the blocking step. What does it do to physics? Well, nothing if you consider the infrared properties, the physical properties. For example, if I take a correlation function, let's say between this original point and this original point, then I take an average here and an average there, that is like this blocked spin and this blocked spin, and take the expectation value or the correlation of those two fields. It is relatively easy to show that the correlation functions between the original and the new blocked fields really just differ in the amplitude. The exponential decay remains the same. In fact, I wrote it down as an exercise to show that explicitly. This is a statement that's valid if X is large, that is, I place if I consider the two fields that I correlate far away, so the actual block size is much smaller. So the requirement is that the block size is much smaller than the distance between the fields. So if the correlation length does not change, we know we expect it to decay exponentially at e to the minus x over psi, that I can write x over a over psi over a. Now, what happened with the lattice spacing here? The lattice spacing was just the distance between the grid lines here, and let's say I had a correlation length psi. Now, the correlation length is still the same here. I have the same psi. And the lattice spacing is also the same because I haven't done anything to this system yet. But imagine to somehow rescale the lattice. So I really just keep the blocked lattice and make it shrink together. That is, I rescale the lattice spacing to 2a. Then if the lattice correlation length will decrease by a factor of 2, because now in the 2a unit, the correlation length is half, and the exponential decay of the correlator will know about it as well. It will be x over 2a divided by psi over 2a. This is a step that I could illustrate with this picture here. That is, I start from the blocked system that still had lattice spacing A, move it to a system that now will have to have a lattice spacing 2A, but it is back to normal. This is a rescaling or dilatation step in the RG phenomenon. This is the second step of Wilsonian RG. I wrote it down again. Just summarize it. That is the second step is to rescale all physical quantities with the scale change B. Now, the physics, the infrared physics does not change under this transformation, but the action will. Imagine that when I formed, let's go back to here for a second, when I formed these block spins that lead to the block spins on the right side, I have only nearest neighbor interactions. But the two green points will include interactions from here to here, for example. That's a non-nearest neighbor interaction. I will have to invert that, but at the end of the day, it will lead to interaction not only between nearest neighbor spins, but for example, diagonal or next to nearest neighbor interactions. That is, the action itself will get much more complicated. This is similar to what we discussed last time when I said that when we had the example that you can take the derivative and express it as a 2-point derivative, or take a derivative, express it as a 5-point derivative. You can easily describe the same continuum limit with a system where only nearest neighbors interact versus distance 5 interact. This is similar to that, but in a very controlled way by integrating a time momentum mode. So what will happen? Let me try to do a cartoon here of the action space. And what I mean on action space, it could be nearest neighbor interactions, next to nearest neighbor interactions. Maybe we had 5 to the 4, we can generate 5 to the 6. All those interactions form an infinite dimensional action space. Now, originally, we have only one parameter, let's say the temperature or the coupling lambda in that system, and we might have a critical point right here where the correlation length is infinite. Now, once we start doing this blocking transformation, we generate other couplings. Let me call it, let's say, lambda 2, lambda 3, and you can add to it. There are infinite number of them. Once I extend my action space from one parameter to 2 or 3 or many, what happens to this critical point? Well, it also extends. It will, in fact, if you think about it, it will turn into a surface. So we'll have a critical surface, and our critical point of the original action is just one point on that critical surface. So again, what happens? For example, if you do a simulation where we start somewhere away, not right on the critical surface, let's say we start at this point in our simulation and then, or in our system, and then we do a block transformation, an RG block transformation. This point will move somewhere in that multi-parameter action space. We don't know a priori where it will move, but we know if it will get away or closer to the critical surface. So think about it. If I started from a correlation length psi and I do an RG transformation, that will take psi to psi over 2, that's further away from the critical surface than the original point. So maybe I will move to somewhere here, where the correlation length is psi over 2. If I repeat it, I might go here with psi over 4, and so on. That is, after RG blocking, will move away from the critical surface. What happens if I start on the critical surface, like here? Then infinite is infinite, even if I take half of it or a quarter of it. So from the critical surface, the flow will stay on the surface. For example, it might go to here, to here, to here. There is no proof, but good evidence that this kind of flows will actually run into a fixed point on the surface. That is, the RG transformation can have a fixed point where the flows on the critical surface run. That's why do I call it a fixed point? If I started from my original action, I will run to the fixed point. But if I start from somewhere else, I still run to the fixed point. And anywhere else, the flows will run to the fixed point. So this is the general picture that we can not prove, but reasonably argue that will happen. Now, let's look at these RG flow lines a little bit closer. So this is the same picture. Let me just put the critical surface around the critical point, find the fixed point. The flows run into the fixed point. And so let's distinguish. I am talking about critical points that is simply a phase transition point with psi infinity. That could be any action that I simulate that is a phase transition point. The fixed point is something different. The fixed point is a specific point on the critical surface that the RG transformation is stable. If you prefer to see an equation, this is the setup. That is, if I denote my coupling by lambda, an RG transformation takes lambda to lambda prime, then lambda prime is not changing under the RG transformation. That is when lambda at allocation lambda star, that's what we call a fixed point. So here we have a fixed point. Again, I didn't prove it, it is just an assumption. What happens now, and then these red lines that I'm drawing on the critical surface, I can call them renormalization group flow lines. They describe how the action changes under RG flow. Now, what happens if I start not on the critical surface, but close to it? Again, one can argue that the flow for a while, well, first of all, off the critical surface, as we discussed, the correlation length decreases, so it will go away, will leave the critical surface. But if we start close to the critical surface, for a while it will go along the critical surface before leaving it. In fact, we have a specific direction that if we start very close but right at the fixed point, the flow will go along a very specific trajectory. That's what we call renormalized trajectory. And if we have a flow that is starting not on the critical surface, but close to it, it will first follow the flow close to the critical surface. It will run close to the fixed point. And then once it gets to the fixed point, it will deviate and start approaching the renormalized trajectory. The way it approaches the renormalized trajectory can be predicted. Again, this is the hand-waving picture that I like to think about. A flow will run either to the fixed point or will flow close to the fixed point and then go away in the renormalized trajectory. Of course, the renormalized trajectory exists on the other side of the critical surface as well. Now, in the vicinity of the fixed point, we can linearize and diagonalize the RG equation. We can find the lines, flow lines that have a negative value in the diagonalization. Those are irrelevant operators. That is, that they approach the fixed point, or they could have a positive exponent, and in that case, they flow away from the fixed point. That is those are the relevant operators. So this guy would be a y larger than 1, while these are y less than 1. Okay. I have an example on the next page, but let's stop for a second. I don't know if you have seen this kind of discussion of renormalization group flows or Wilson RG, or in general. It doesn't have to be Wilsonian RG, it is just in general when we have flows that have fixed points, like sources or things, that the flows can go into the fixed point, can flow away from the fixed point. Does it make any sense? Are there any questions? I don't want to go on if that picture does not quite make sense. But if no one is shouting, I will assume that, yes?
Just because it's fun to connect different talks, I'll make a comment on the description of a
Okay.
I'm correcting it, but I'm just pointing out something which is back in history. There were people, Catterall, Migdal, and so on, who use this on the Ising model, which is, of course, the child that bootstrap people love to look at. And if you truncate, if you do it by quote decimation, you somehow it spins, and you just truncate the number of terms, which of course you've done already. You said you have so many axes, right? But you can do it just like the bootstrap and decide that, well, I'm going to have 3 terms or 4 terms. And there's various ways to do this. So then you can write down algebraic equations that show when you, and if you keep the pattern fixed, right? So every time you do this, you get another lattice with another set of patterns and so on. So you can write down various approximations. If you do this, you get recursion equations. And when you go to the fixed point, you get a matrix. And when you look at the eigenvalues of the matrix, those are approximations to the dimensions of the operators. So you can actually calculate without the bootstrap, this sort of geometrical approach. And there were calculations, reasonable Ising models. So the point that this truncation is analogous to the truncation of the bootstrap of asking how many operators you're going to keep. And this is a recursive way to see how, and as Anna's shown, that in the Ising case, there's only one unstable direction. That's the lowest operator. It's usually called, what do you call it? Delta epsilon, I guess you call it. Anyway, so the point is, it's a fun game. It's very simple. You can go look at it, and you can do it on a piece of paper and show you that you're actually looking at the anomalous dimensions of various operators as approximated by terms in the action.
Good. Thank you, Rich. That's exactly it. If I had heard any of the lectures yesterday, I might have even remembered to call that. Indeed, whether we truncate or not, this is a truncation because I can't draw more than 3 dimensions on a piece of paper. But indeed, the setup is the same. We have a fixed point, we diagonalize it to find the eigenvalues of the diagonalization, find irrelevant or relevant operators. And I have an example here. It's an old one, Bangalore 1975. It's an RG transformation for the 2D Ising model. It's an approximate one where only 2 terms are considered, a nearest neighbor and the diagonal term. And the RG equations are solved in that truncated approximation. And what the result shows, let me try to explain what is what on this picture. K1 is the nearest neighbor interaction. So if I take this axis right here, this is just the good old ordinary 2-dimensional Ising model. It has a critical point right here. K2 is the diagonal interaction. And if I take a system that has only diagonal interaction, that's this line here, that also has a critical point denoted by here. Now I can allow negative interactions that will take me to antiferromagnet. So if I go negative in K1, there is an antiferromagnetic interaction with its own Ising-like fixed point. In the diagonal term, the negative will be, again, there is a analog fixed point there. So this is not unexpected, but let's see what happens to the critical surfaces. Let's pick up another color here. It turns out that all these fixed points are connected by these critical surfaces that you see here with black lines. There is 2 critical surfaces coming out from the positive K2 fixed point and then just 1 from the negative one. The surface here, this is the surface that we usually talk about when we talk about Ising model. The fixed point is this guy right here. And the arrows that you see here refer to exactly, this is the renormalized trajectory, a positive relevant operator both directions, and the other directions are negative. It repeats itself in the antiferromagnetic direction, and then this lower line is actually interesting, that's a different phase. But that was done in 1975, no computers, just a truncated approach, and I repeated a couple of names who were working on this kind of system before. So maybe it's a good idea to think about Ising model and bootstrap because it's the same physics, it's just a different description. Good. Questions from the students, or you are happy with the explanation now? If so, I would like to go on to what I really wanted to do. So do a very quick recap. I did a very quick, probably not fully understandable, but hopefully enough introduction to Wilsonian RG that you can sit down, think about it. The important thing I would like you to remember that Wilsonian RG removes the UV part of the system at the price of generating all possible action terms, so it extends the action to infinite dimension. Fortunately, the fixed point and its renormalized trajectory are the only things that matter for the continuum physics, so we don't have to worry about all the infinite dimensional action space. And how do we connect this system to continuum renormalization, like Kellen-Simontic equation or the continuum beta function? You can think about the lattice parameters as bare couplings at the cutoff level. The lattice is really just, it has a cutoff. The parameters we put in there, the lambda, the G0 are cutoff level parameters. As the renormalization group progresses, as we do more and more RG steps, the cutoff decreases at every level by a factor of D. So eventually we'll go down to low energies. We can denote it by mu. At the same process, the parameters of the action evolve. And if we take the relevant parameter, which I will just call here by G, that relevant parameter, if we follow it along the renormalization group flow, that will correspond to what we call the running energy-dependent running coupling in the continuum. So that's how we recover the continuum description. And at this point, we could even take this coupling and take its derivative to get the beta function. So in short, when we do a lattice system, when we discretize, that provides a regularization that is regulates the integrals, and then we do the RG transformation. That gives us the renormalization scheme. Very similar to the continuum, but we really separate here very clearly of what is what. Again, how we think about it in continuum versus Wilsonian RG. In the continuum, if we know how many relevant operators there are, like 1 in a gauge system, 2 in a 5 to the 4 system, we keep only the relevant operators and don't bother with the rest. In the Wilsonian RG, we keep all the operators, but we'll see which ones survive the renormalization group transformation. So there is really a back and forth. We know how to connect the continuum and Wilsonian RG. We do Wilsonian RG on the lattice because that's what naturally fits the description. Good. So I showed you an RG transformation and critical surfaces for the Ising model here, but I really would like, I am really interested in QCD-like systems, 4-dimensional systems, as we discussed last time. So let's see if we can connect, if we can figure out, based on the beta function that we know perturbatively, what the corresponding multi-action parameter space flow diagram should look like for the QCD-like system. So let's think about it. This is the beta function. You remember what the beta function is. It is just mu dg square over d mu. When it is negative, that means that when we change, okay, actually, let me write it the following way. When the beta function is negative, it means that if mu decreases, that is, we go from high energy to low energy, then g square has to increase. That is, delta mu is negative, then delta g square has to be positive. But it means that if I start from here, let's say this is my cutoff, and I go down in energy towards some physical energy scale mu, the change in g square is to increase. That is, we understand that that's what asymptotic freedom actually means. How does that look in the multi-dimensional action parameter space? If I have one relevant operator, I denote it by G1. And I can put in all the other operators, G2, G3, those are irrelevant. The critical surface now, if I have a fixed point here, that means that this surface here is critical. That is, the critical surface is at G equals 0. That's the relevant operator 0. Then I should have a fixed point on that G1 equals 0 critical surface. We typically call this fixed point Gaussian fixed point because it's at 0 coupling. Then this on the RG picture, there is a renormalized trajectory that emerges from that Gaussian fixed point. And when we do simulations and RG flows, if we, for example, take a point as our simulation point, it's a bare action point, the RG flow will first flow towards the fixed point and then flow along the fixed point and then flow along the renormalized trajectory. If I take a different bare action, bare parameter value, again I flow towards and then along the renormalized trajectory. So that makes sense. We again have, just as in the continuum, a flow along the renormalized trajectory to increasing G-square values. Now, the important thing to remember here is that the renormalized trajectory itself has no irrelevant operators. It really is just the one single relevant operator changing. It describes continuum physics. And if you think about the flow along the renormalized trajectory, that's exactly the flow that is described by the continuum beta function if it is properly renormalized. So that is the connection. In the continuum, we have only one parameter, a relevant operator G squared. The movement or the change along the renormalized trajectory in the Wilsonian language on the lattice corresponds to that description. And now you can, we have recovered of one relevant operator. The fixed point is the perturbative fixed point. And simply when we do simulations that don't start on the renormalized trajectory, that means that we have irrelevant operators that will die out as we run the renormalization group to lower and lower energy. Again, we also understand what this cutoff means. Cutoff is basically what our direction is. And then one comment here, that imagine that we know from physics, from experiments, that the value of the renormalized coupling at some energy scale is given, like alpha strong in QCD. How can we achieve that alpha strong in the infinite cutoff limit? Well, we want to achieve arrange things such that no matter where we start at a cutoff, we always end up at the same point as we run to lower and lower energies. What that means is that if we increase the cutoff, we simply have to start further away from our desired value or closer to the Gaussian fixed point. That is what we refer to, that we can, if we want to keep the gauge coupling fixed at a physical energy value, the infinite cutoff limit can be achieved or has to be achieved by tuning the bare gauge coupling to 0. That is again here. If I always want to end up here, if I want to run the RG transformation longer and longer, I have to tune the bare coupling towards the critical surface. Again, that's the identical statement that the continuum limit is when psi is tuned to infinity. Good. So this is QCD. You see the analog. What happens if I have a conformal system with a beta function like that? Now, again, the RG flow where the beta function is negative is going to larger and larger G square. But it cannot go to arbitrary large value, it will stop here. That's the meaning of the infrared fixed point. On the other side, where the beta function is positive, the flow is just the opposite direction. Again, it flows and it flows into the infrared fixed point, it cannot go any further. How does that look in the Wilsonian language in the action parameter space? Exactly the same. We have the Gaussian fixed point, just like before. We have now an infrared fixed point, and the flows will run into the infrared fixed point from both directions. So actually this side I probably will have to redraw, but you get the idea. Again, the continuum physics is whatever we find on the renormalized trajectory. Let's see if we can come up with an idea, with a picture of what happens in the infrared free system. That is when we have so many fermions that the beta function flips time. Now the beta function is positive. This means that the RG flow is always towards smaller gauge couplings. It runs into a fixed point, the Gaussian fixed point. It is still a fixed point. But is this fixed point relevant now? It's not. The flow runs into it. So if I want to try to draw the picture as I did before, this is G, the relevant operator. This is G1, G2, G2, G3, the irrelevant operators. I still have a Gaussian fixed point. I might even identify a renormalized trajectory, but now the flow is going back in. And if I start from a finite value of the gauge coupling, the flow will run towards the trajectory and then along the trajectory. That is, it will run to zero. That's why we call it infra-free, because no matter what we do, no matter where we start, and that could be even up here, it doesn't really matter, the RG flow will run to the Gaussian fixed point where G is zero. We cannot avoid renormalized coupling G squared being zero. That is what it means. It's an infrared free system. Now, yesterday I entertained the idea that maybe this asymptotical or infrared free system develops actually another fixed point like here. Now, what kind of fixed point is that? Is it relevant or irrelevant?
Can I ask a question?
Mm-hmm.
Is the reason to choose this surface on the G2, G3 plane at G square equal to 0? You want correlation length infinite. That is the reason?
Actually, no. So if you think about it here, the correlation length is 0.
Okay.
A fixed point can show up either at 0 or at infinite correlation length, because we know that under RG, psi will go to psi over B. So if I have a fixed point, that means psi star will have to go to psi star over B. It has to be identical. That can be either with 0 or infinite. So in this case, it's a very good question. The correlation length will be 0 on that surface. It's not a, it's not a critical surface, it's a trivial surface.
Okay. What if we have some finite correlation length? So I think in that case, that surface will shift to some finite value of G1.
Say that again, I didn't understand what you said.
What we have, if we have finite correlation length for some non-zero correlation length,
then there is no fixed point.
okay.
If you have a non-zero correlation length, then it will decrease as we do RG. It cannot be a fixed point.
Okay. So in this case, there is only one surface that will exist in this setup, or there may be another surface.
So that's actually the question. We don't know. We don't know the answer, and that is what this possibility that I drew here could be. If let me say it in this way: if I have a beta function that really is just like that, positive, and doesn't have a fixed point, then this system is trivial. What do we mean that it's trivial? That I can try to start with a stronger coupling, large G square, but doesn't matter where I start in the low energy limit, I will automatically run towards 0, and there will be no interaction left.
Okay.
Now, this happens in this case if I have many fermions, but it happens in another situation that you might recall that is more relevant to physics, and that is in 4 dimensions, the 5⁴ model has a beta function that is positive that we can calculate perturbatively, and people actually spent a lot of time trying to figure out if there is another fixed point in that system, like the picture I drew underneath, or if the beta function stays positive all the way to infinite coupling. And it turns out that the 5⁴ system is in 4 dimensions is indeed like that. That is, it doesn't have another fixed point. It doesn't have a critical surface. It is just a trivial system.
Okay, thank you.
But let's entertain the idea that what if the gauge system has another fixed point? Now, if it has another fixed point, that is a UV fixed point. It's where the gauge coupling is relevant. It is pushing away the gauge coupling in both directions. And in that case, this is a gauge coupling, but this is a point where the correlation length is infinite, and there is a corresponding critical surface for this setup. So if I have this situation, then I should have a critical point on the g-axis. There should be a critical surface associated with it. And then that also means that there will be a fixed point, an ultraviolet fixed point, where the renormalized trajectory that runs into the Gaussian, trivial Gaussian fixed point starts. Does it happen? Well, we don't know. People have tried, and these are relatively new investigations. I will try to add some references later on. There are calculations in large NF, large number of flavors, that suggest that the system actually has an ultraviolet fixed point. This ultraviolet fixed point is sometimes referred to as asymptotic safe. Fixed point or asymptotically safe system. If that happens, that would mean that we have a new critical point with its associated fixed point that describes physics that we do not see perturbatively. Perturbatively, we really understand only this section of the beta function. That's what we can achieve, or this part of the system.
A question. It's very interesting. By the way, I was very impressed that as soon as I made the remark, you had a slide already to answer the remark. So that's it. And it was better than my remark. But at this other ultraviolet fixed point, does it mean there are really two theories? If you were at the left of it, it would run to a trivial theory in the infrared, but there could be a new theory to the right of it, right? That could be a new confinement.
I think it doesn't necessarily run to the infrared, to the trivial theory here. Just like in a conformal system, we can keep the flow to the Gaussian fixed point, and it does not run to the infrared fixed point. Here as well, if we tune
But I thought if you went to the right of this thing, then you would be repelled. You could treat it as an ultraviolet fixed point. And wouldn't there be another theory to the right?
No, there would be two theories. I fully agree with that. I can define a theory both to the left and both to the right. It would be like an Ising model in the broken and symmetric phases.
This is sort of like Reinbard's idea of having gravity with some strong coupling fixed point that you would have to.
Yep, exactly. Exactly. It is the same thing. In this setup with large number of flavors there were a series of papers a couple of years ago by Francesco Stanino and collaborators, where they predicted it. They tried to see it on the lattice. I even tried to see it on the lattice. I could not find a fixed point. So it might not exist, but it's an interesting possibility. And if it doesn't exist here, it might exist somewhere else. So why did I mention it? Because now we went through almost all the possibilities of what the beta function can do and what it means for a lattice simulation. The important thing is that UV fixed points always come on a critical surface, while infrared fixed points, there the correlation length is 0. They are not associated with criticality. And if you have the beta function in the continuum, you can guess the RG flows on the lattice. It's a guess, but usually after a while we get good at guesses and vice versa. Good. So let's see. I am looking at, I have about 10 minutes. I don't want to make the mistake as yesterday that I was going to go on for another half an hour. But let's look at something, actually this one, good, different. You recall this beta function I drew yesterday and even showed it today. This is an analog, or not an analog, I'm sorry. This is an alternative of the conformal fixed point. So perturbatively, then we have a conformal system. The conformal fixed point shows up at infinite or very large coupling, and then eventually moves in to smaller couplings until it disappears and turns into infrared freedom. That is the perturbative description. It has been hypothesized by several people that that's not the only way to achieve conformality. We can have a conformal system where the beta function develops a hump, and when the hump just touches the axis, that is a fixed point, that it develops a fixed point. It's a special fixed point if you think about it, because the flows go into the fixed point from the left. So it looks like an IR fixed point, but from the right, the flows go to the right, so it looks like a UV fixed point. This is a fixed point that is typically, not typically, but might be associated with a Kosterlitz-Thaler-Berezinski type of fixed point, like the two-dimensional XY model. Again, whether it actually occurs in four-dimensional or not, it's an open question, but it's certainly an interesting possibility. Now, if this is how the conformal window opens up, then you can imagine that the next, if we increase the fermion number further, this fixed point will be, or this beta function will be pushed up to the positive, and now we'll have two fixed points. This is what I have on the picture on the right. So let's look at it. It's a little bit better described. So this guy, the red point, is the opening of the conformal window, and the other two are within the conformal phase. But now it is really interesting because how many fixed points do we have? We have the Gaussian fixed point here, we know that. This fixed point here is an infrared fixed point. The flows run into it from both directions. And then this guy here is new. This is a UV fixed point. It's a UV fixed point into both directions. Just like the fixed point I discussed here, this guy here. So if this is the scenario, we have the riches. We have the Gaussian fixed point, the infrared fixed point, and yet another UV fixed point. So how would I draw a phase diagram on the lattice? I can try what I did before to say this is my G-axis, the relevant operator. There is the Gaussian fixed point, the infrared fixed point, a UV fixed point flowing in, out, in. But think about it, a UV fixed point always implies a relevant operator. In this case, when I drew this picture here, this relevant operator is, I still denoted by G. But we know from the Wilsonian picture that as soon as I start doing RG transformations, I will pick up an infinite number of new operators. In fact, it is very unlikely that the new relevant operator is the same as the gauge coupling. In fact, it is much more likely that there will be a new relevant operator. I'm going to denote it by capital G. And what could be this new relevant operator? It could be some kind of, for example, fermion operator. At least that's what the people who came up with this hypothesis were suggesting. And I will show why that is indeed a possibility. Now, if that is the case, then I really should put my phase diagram such to include this new relevant operator. And then, of course, I can have other like G2 that is still irrelevant and capital G2 that is irrelevant. But the main picture is that I should include, in addition to the gauge coupling, a new relevant operator. So now let's go about it. Let's try to figure out what the phase diagram could be. We know that from the Gaussian fixed point, the flow will, with a relevant operator, the flow is going away. Now, I have a new fixed point, a new UV fixed point. There has to be a critical surface associated with it. UV fixed points sit on a critical surface. Well, that would be the most general critical surface. It's a psi infinite critical surface, and my new UV fixed point would be sitting here. Now let's try to finish this diagram now. If this is a UV fixed point, the flows go away in both directions. The flows from the Gaussian fixed point also go away. So it's reasonable to say that there is an infrared fixed point in between. And basically the RG flows or the renormalized trajectories are such that they start from the Gaussian fixed point, run into the infrared fixed point, and then on the other side connect to the UV fixed point. Now this is a beautiful setup. What do we have here? We have here a conformal regime. But that conformal regime has a UV fixed point. If I tune to that fixed point, it will describe the renormalized trajectory in this sense, in this regime. But even more interesting is that there is another relevant direction on the other side, and that an yet unknown, ununderstood, possibly new phase structure or phase. We don't know if it exists, We don't know if it exists, what describes it, but that would be a newly emergent fixed point with its yet perturbatively undetermined or unpredictable phase. So I would like to talk about it a bit more, but I know that I have only 3 minutes, and I promise that I won't go over time today. So let me just finish this picture here. So if this is my critical surface, I can ask what happens to it. Is it going to hit the gauge fermion axis? And if it crosses the gauge fermion axis, I still can ask what is the order. This is certainly a second order phase transition, but we have seen many times that a second order phase transition can turn into first order. If that happens, there is no way to study the fixed point just by looking at the gauge system. On the other hand, if this is not first order but continuous second order, then I should be able to study the properties of the UV fixed point if I can look at the gauge system at strong enough coupling. That is a very interesting possibility, and I will talk about it perhaps starting tomorrow and then next week. Now, I would like to stop today with a set of exercises. I already listed a few, but I have a couple of more if anyone wants to get some more practice of Wilsonian RG. The first suggestion is a relatively simple problem, namely take the one-dimensional Ising chain, that is a system that has Ising spins along a circle, a periodic boundary condition, and try to work out explicitly what happens when we do an RG transformation. And what would be an RG transformation? That we take these two spins and replace it with a new spin, and then take these two spins and replace it with a new spin, and so on. So with that way, this is the reducing degrees of freedom, but now in one dimension, you can actually work it out explicitly. And it's interesting to see how the action changes. You can find the correlation length. You can ask if this system has a fixed point. It will not have. We are not that lucky, but it's an example that you actually can work through on a piece of paper. Now, once you understand that, you can try to do it in 2D, and that will get messy very, very quickly, but you probably can do 1 or 2 steps, and that will show you how diagonal next to nearest neighbor and higher order terms emerge. And then at some point, one has to truncate that. That is what the examples in the Ising model I showed you were done with. But these are just some very straightforward examples to get an idea of really how this entire renormalization group works. So I'm going to stop here because it indeed is, I assume, 11:15 for you and 11:45 p.m. For me, but I am happy to answer questions.
Thank you, Anna. That was great. Let's see if there's any questions.
Can you comment on the location of IR fixed point if we have a theory with IR cutoff? So in that case, IR fixed point will be between the IR cutoff and UV cutoff or below the IR cutoff?
Okay, so it's a good question, but I have to step back. And part of it is that I didn't cheat, I just didn't emphasize that when, let's go back to the gauge system here. When I drew, even in the gauge system, we actually have 2 relevant operators in general the fermion mass and the gauge coupling. And if I have two relevant operators, then the Gaussian fixed point would have two directions where it flows away, both in the mass and in the gauge coupling. The picture I drew here is valid only when I set the fermion mass to 0.
Okay.
And that is also valid, also true when I do RG conformal systems. This picture is valid when I restrict the description to one relevant operator. And if we have another one like the mass, then I set that mass to 0. Now, if I have a system with an infrared cutoff that you have to ask how does that cutoff show up physically, and how do we handle it? Basically, we handle it by not running to 0 energy scale. But that is just not allowing mu to go to 0, but the fermion mass is still 0. So it's a great question. I have never thought about RG with an explicit RG IR cutoff, but I have the feeling that it is just not a question you can really ask, because when you have an IR cutoff, you have another relevant operator, and you have to rethink the entire setup.
Yeah.
Does it make sense?
Maybe we cannot have this Gaussian fixed point if we have a IR cutoff in the theory, and location of the IR fixed point is above the IR cutoff. Yeah.
But you made another good point that I again didn't mention. The location of the IR fixed point is scheme dependent.
Okay.
And you can see that if you do the perturbative analysis. For example, take 16 flavors, which is certainly IR conformal. Take the beta function with 2, 3, 4, or 5 loop, and calculate where the fixed point is. Naturally, that's not a good idea. You can calculate the IR cut of the fixed point. There will be a fixed point, but that is in an MS bar scheme.
Okay.
If you change the scheme from MS bar to pick something that you can calculate, the value of the fixed point will change. It's non-physical. And it's easy to understand. It's really just that there is no infinite correlation length, no phase transition, nothing special happening at the IR fixed point. The phase transition really happens when we have a UV fixed point like this one, or even better, this one. So where exactly the IR fixed point is not a physical statement, but that is probably the same that if we have an IR cutoff, that depends on the scheme we are using to define it.
Okay. Yeah, thank you.
Mm-hmm.
I don't see any more questions over here, so maybe there's something online.
I don't see anything online, and I know that you are dying to get your coffee.
So let's thank Anna.
Thank you.
Thank
and,
you.
Okay, not tomorrow, but the day after tomorrow, I will continue with pretty much this picture here, and try to tell you, first of all, if we can do anything like that on the lattice, and then even simpler, if we can predict the beta function, either like that or a simpler one on the lattice. So that is the plan for next. That will be Thursday. If you have questions, feel free to shoot them my way, either in Slack or email. Thank you, and enjoy your coffee break.